Okay, so this is a quick recap of page 9 for anyone that missed it. We're talking about intermolecular forces here. That's that IMF column that you've seen on page 5 and 6 that we've left till last. And these intermolecular forces are the forces holding separate molecules together. These aren't actually bonds inside a molecule. These are just the forces holding them together. And we use these to help us to predict whether these covalent compounds we've been looking at are going to be solids, liquids, or gases. Because like we discussed in Unit 4, covalent compounds can be any state of matter at room temperature. And the difference isn't in the bonding holding them together, it's the intermolecular forces and how well the separate molecules are held together. So, the stronger the force, the closer the molecules are held, and the more likely that is to be a liquid or a solid. The weaker forces generally mean that that's not held together very much, and those molecules can separate and go floating off as gases, completely separate from each other. So, there's these two little reactions at the top of the page. There's not really much to do with them. It's just kind of showing you the difference between these intermolecular forces and bonds. You can see if I take HCl and add just a little bit of energy to it, then that HCl can turn from a liquid into a gas. And that's separating the molecules, just getting them farther apart. And that energy that we were adding, that 16 kilojoules per mole, was overcoming the intermolecular forces there. So it's just separating the molecules. It's a physical change because I had HCl at the beginning and at the end. Now, in that second reaction, you see HCl. I'm adding a whole lot more energy to it, and that energy is physically breaking the covalent bond, or chemically breaking the covalent bond. So that's a lot more energy is required, and I don't have HCl at the end, so that's a chemical change that my molecule is going through. So we're just talking about those little forces holding molecules together. And there's three types. The first one, your notes called the dispersion forces, but let's add the word London in front of that to make it London dispersion forces. Sometimes we're going to abbreviate that as LD. And this is just a force that's caused by the movement of electrons within the atom. Sometimes when they're moving around randomly, more electrons happen to be on one side of the atom or the molecule than the other. And because of that, that's going to create what we call an instant dipole. It's only there for an instant, and it is important that you know and remember that this is a temporary dipole. So let's say more electrons are around this side of the molecule. That means this side is going to have a slight negative charge, and this side is going to have a slight positive charge. So that's just for an instant. The electrons are going to keep moving an instant later, and that slight polarity is going to go away. But for that instant, while it has this charge, this positive charge here is going to attract the electrons on this molecule, and they're going to kind of want to squish over and spend more time around that side of this molecule, giving it a slight negative charge, and this side a slight positive charge. But like I said, this just lasts for an instant, but due to the random motion of electrons, we can get these non-polar molecules to sometimes act like they're slightly polar and have this temporary charge where they pull together, and they have this very weak attractive force. Now, underneath there's 3 different bullet points underneath where you drew those, filled in these little ovals, and I know there's a little space between it, but I summarize those here. Firstly, the more electrons a molecule has, then the more strong this London dispersion can be, because more of those electrons might happen to line up on the same side. Now, all atoms and molecules have this London dispersion force. It's present in all molecules, but it's not necessarily the strongest force in all molecules. As long as you have electrons, though, they might happen to line up more on one side than the other. And very important to remember is this last bullet point. This is the only intermolecular force that non-polar molecules have. So if it's a diatomic or a noble gas, this is the only force, intermolecular force holding it together, and that's why those tend to be gases. Now, our second force is a lot like the same, so I'm actually going to take a second to show you this short little kind of video clip of this London dispersion force happening. So, my electrons are moving around the atom, and they're both moving independently, and sometimes randomly they just line up more on one side than the other. So that creates that temporary dipole, and then they keep moving and they goes away. Now, I might have more than one atom with these randomly moving electrons. Independently, they can have these little slight dipoles. But through this random motion of the electrons, if they do happen to all have that negative charge on the same or on kind of opposite sides, there's this weak attractive force that pulls them together. Like we already saw, these electrons are never going to stop. They're going to keep moving. So it's a slight attractive force where these atoms or molecules are pulled a little bit closer together, but then it'll go away. So this is the weakest of our three intermolecular forces because it is temporary. Now, dipole forces is a very similar idea, except this is only going to occur around polar molecules. So our podcast showed us how to tell if a molecule is polar or nonpolar. Polar molecules have this dipole force. And this is just like London dispersion. It's just that this is a permanent polarity. These molecules are always permanent. That's permanent. That's not permanent. Still looks wrong, but we'll go with it. Permanent, not temporary. So these molecules are floating around together with those negative and positive charges. And because that's permanent, as they're floating around, it's going to tend to line up the same way as these other molecules, maximizing those opposite charges that are attracted to each other. And so they kind of form these little units where 2, 4, 10 molecules might kind of stick together because they happen to line up the right way. You can kind of imagine if you had a bucket full of magnets. Even if you put them all in there separately, some of them are just going to happen to be oriented the right way that they're going to stick together, and then they're going to go floating around in that basket of magnets together as a unit. So, permanent polarity forms this attractive force. This is stronger than London dispersion because that charge, that attraction doesn't go away. It's going to stay there. So this little video kind of shows us what happens as these molecules are moving around together. I'm going to try and get this to play. And this first part's a little slow, so I'm going to skip ahead. But if these molecules do line up positive to positive, there's no attraction. There's a little repulsion. It might give it a little bit of a push. But as soon as it lines up positive to negative, and especially if it has this double attraction here with 2 positives and 2 negatives, they're going to be moving around together and forming this unit and floating around in that substance together. And there's going to be other molecules in that substance that are also floating around in these little units because they're attracted to each other. Now, as I heat up this substance, it gives the molecules enough energy that they can start to break apart from each other. And they might go find another group to grab onto, or if we give them enough energy, they might vaporize or boil and go off and join the gas phase after we hit a certain temperature, though. Now, if we compare this polar molecule that we've been looking at to some non-polar molecules at the same temperature, that non-polar molecule is more likely to boil because it doesn't have that attractive force, that permanent attraction to the other molecules. So these 2 different liquids are at the same temperature, but the non-polar one just has London dispersion forces, is boiling, while the polar one is not because it has those extra dipole holding it together. Now, our last type of intermolecular force is called hydrogen bonding. Now, this is still not a bond, but in order for hydrogen bonding to occur, you have to have hydrogen bonded to one of these 3 elements, N, O, or F. Or the way I remember it, and I know it's silly, you can't hydrogen bond without a phone. You can't talk to your friends and bond with your friends without a phone either. And you can't hydrogen bond without a phone. It's just this phone is fluorine, oxygen, or nitrogen. So that's all we're looking for is hydrogen, first off, and it has to be physically connected and bonded straight to one of these elements. It can't just both be in the same molecule. They have to be bonded together. So water has a lot of really strong hydrogen bonds because all it is 2 H's directly bonded to an O. That's one of the things that makes it so super polar. Now, at the bottom of the page, this is the type of questions you're going to be asked about our intermolecular forces. I'll give you a formula, and I want you to identify the type of IMF that they have. Now, some molecules will have more than one type. So really here, I just want the strongest type of intermolecular forces. And because I want the strongest, it helps if we start from the strongest. Those hydrogen bonds are the strongest intermolecular force. Then our dipole, and then our London dispersion. So we're going to start at this top and ask ourselves, does CH4 have hydrogen bonding? Well, it does have hydrogens, but there's no F, O, or N, so there's no hydrogen bonding there. And dipole-dipole is only on a polar molecule, and if we look at CH4's structure, you'll notice that there's no lone pairs on the central atom. All the atoms around the outside are H's, despite this one not looking like an H. So there's no different atoms around the outside, so this is not polar. So that is not an option. It's not dipole-dipole. So the only option left is London dispersion, and that's going to be the choice that we make here. So this is London dispersion forces. H2S. Does it have hydrogen bonding? I've got H's again, but once again, there's no F, O, or N, and we can't hydrogen bond without a phone. So that's not the best option. If we look at the molecule H2S here, then it has these lone pairs on that central atom, and so that is polar. So that means it does have dipole-dipole forces. So that is our major force for H2S. Then H2O, we have hydrogen bonding happening because H's are connected to the O's. And I could draw out that structure, but there's really nothing else for them to be connected to. So H is directly connected to F, O, or N, means that we do have hydrogen bonding happening here. Clean this part up a little bit. So start at the strongest and work your way down. That's all that we want to know, is the one strongest force that substance has in order to label it in this table. Now, this asks us one more follow-up question. Which of these would we expect to have the highest boiling point? Well, whichever one has the strongest intermolecular forces that are being held together the most, and hydrogen bonding is the strongest. So H2O would have the highest boiling point, at least of these options. We know ionic and metallic have much higher boiling points than covalent, but out of these covalent options, water, dihydrogen monoxide, does have the highest boiling point. Now, I'm going to real quick go through pages 5 and 6 with these IMFs just so you can get those examples. If you got this, you can probably do it on your own and just check for the answers. So here we see hydrogen connected to F, so that's hydrogen bonding. H2O, hydrogen is connected to O, so that's hydrogen bonding. CH4, hydrogens are not connected to F, O, or N, and this is non-polar, and so this is London dispersion. In fact, in our notes, what we said was a non-polar molecule only has London dispersion. So if I already know this next one, CCl4, is non-polar, then I'm not going to go anywhere else. It's instantly London dispersion. NH3 is hydrogen bonding because we have hydrogen connected to those nitrogen. And then CO2 is non-polar, instantly London dispersion. In fact, these next two are also London dispersion because they're non-polar. On page 6, HCl, I have an H, but it's not bonded to F, O, or N, so there's no hydrogen bonding happening there. Dipole-dipole is only there if it's polar, which it is. So this is dipole-dipole. SiO2, non-polar, instantly London dispersion. Methanol, even though I have a lot of hydrogens connected to that C, I do have one hydrogen that's connected to that oxygen. So that is a little bitty bit of hydrogen bonding. Not as much as in water, but it does have hydrogen bonding there. Chloroform does not. That hydrogen is not connected to F, O, or N, but it is polar, so that's dipole-dipole. Formaldehyde, I have H's and O's in the same molecule, but because they're not bonded together, there's no hydrogen bonding happening there. So this is polar, it's just dipole-dipole. Same thing with HCN. They have to be physically connected and bonded to each other. Hydrogen has to be bonded to that phone in order to have that hydrogen bonding happening. And then I see 3 more nonpolar molecules, so I got 3 more London dispersions to finish things out. So that should finish up page 5 and 6 for you. And I guess now you got these structures just in case you didn't have them before. Polarity here, if you want to check what you did in your polarity podcast or after it. That's what we did together in class. Hope it helps.